yeah.
respond to your name,
Yeah.
they can send that on.
So I send this separately. Okay, great. I'll take care of that. May I erase this? Yeah, everybody wrote this down? Somebody wrote this down? I wrote it down, so. Okay, let's talk about it. Not the one of the week, the one in red. All right. Let's talk about, so what is the effect of the load, the external load, on the velocity of contraction in Y? What did you find? All kinds of stuff on the internet. Somebody knows, Megan.
The heavier the load, the longer it will take to contract.
Yeah.
The latent period will increase the time between when the muscle is getting the signal and when it actually contracts.
Yep.
Because it needs to recruit more motor units in order to pull.
So latent, did everybody hear that? So the heavier the load, one of the reasons why there's a slowdown is because the latent period increases, because the number of signals coming down the pike have to be greater because you have to recruit more, what did you say? Motor units, which you haven't talked about yet. Okay? So there's a graph in your book that looks like this, and I'm just going to regenerate it real quick. It shows the shortening velocity. And this is the load. All right? And the way they have it drawn here, I guess I'll draw it the same way. They make a couple of nuances here. That's why I'm looking, because I don't normally make these nuances. So, that would be. Okay, so this is in your book. I have an older version with me right now, so it's not going to match up, but it's in chapter 9. All right, so this is a classic curve in muscle physiology that explains the relationship between force, velocity, and load. All right, so the velocity is on the y-axis here. Along the x-axis, you're talking about the load. And you're also on the y-axis below here. So you have a double y-axis. You have a lengthening velocity. Okay, and we'll explain what that is in a second. So the maximal velocity that you can move anything with is the muscle is no load, right? Your unloaded muscle is going to be faster because of what Megan said. Because you have the least amount of motor units that need to be brought into the picture in order to move whatever it is you're moving, the muscle. Okay? As you begin to add an external load, look at what starts to happen to the velocity. It starts to decrease. And then this point here, so this is all isotonic contraction. Isotonic means that the muscle is using the same amount of force. The tone of the muscle is the same. Isometric means that there's no movement occurring. That's at this point here. Okay. Isometric is, and then you have this end of the curve down here is looking at what happens when you exceed the isometric contraction point, meaning that whatever the load is heavier than what you can hold, right? It's beyond maximum. And so what happens is your muscles are trying to contract, but they're lengthening while they're trying to contract, right? You're trying to, what's actually going on here is the load is so heavy that even though you're physically trying to contract, the muscle is actually getting longer. Okay? The muscle is actually getting longer. And the speed that is occurring, the velocity here, is actually greater than here. Okay? The speed is actually greater than here or here. It's not greater than this, but it's fast because of this. You can look at the slope here. So if you look at this slope and you compare it to all the other slopes, where it is greater, basically from here on down, this is faster. Right, that's an important point to make. So as the load goes up, the speed will go down, assuming what? Assuming what? As the load goes up, the speed will go down, assuming what? The key is right here. Michael? As long as it's an isotonic contraction. What if you recruit more motor units? Can you get the speed to go faster? Of course you can. Right? Of course you can. So it makes a difference as to how many of the motor units possible to recruit are being recruited. If you're at maximum, right, then the curve looks like this. But if you're not at maximum, the curve will look different. So this is maximum in this case, meaning you start here with the maximum and you keep a maximum all the way through. If you started with 50% here, right, you'd have a curve. And if you started with 25% here, you'd have a curve. But then you could change it. Does that make sense to everybody? That the speed could change if you could recruit more motor neurons, assuming you're not already at max. If you're at max, then by definition, that's it. There's nothing left to recruit. There's no 115%. 100% is everything. We sort of get, this is a language thing we got going on now in society where it's, I'm going to give 120%. That's utterly ridiculous. If you think about that, you can't give more than 100%. Right? There's only one of you. That means all of you is 100%. I give 120 of you, you'd have to add pieces on. You're not a transformer. Right? You can't do that. Right? You can only give 100%. So 100% is maximum. Does that make sense? Is there any questions on that? This is an important curve in muscle physiology because it explains a lot about the relationship between shortening velocity and load. Now, the amount of force that you can apply in an isometric contraction actually exceeds the amount of force that you can apply at maximal isotonic contraction. So the amount of force that you can apply when the muscle doesn't move is actually higher than that you can apply when the muscle moves by about 15 to 20%. The example would be if you could squat 100 pounds, and that is your maximum squat. You start to the top, you go down, you come back up, then isometrically you could hold 120 pounds, if that makes any sense. Right? Isometrically, you could hold 120 pounds. Questions on that? Does that make sense to everybody with that, what I just said, or am I speaking Chinese? Yeah.
Why is that?
Because you're locking everything down. So the example of this were to be, all right, you have a situation like this. You've got a guy, and this is my stick figure drawing, right? And this guy or girl, we'll make it girl. Okay, it's a girl. Fine. Okay, you're going to make it a girl, and she's on the floor. Okay, she's on her back. And over here, she's in a power rack. Okay, over here she's got, there's a barbell, right? So you can see the barbell here. Okay, the amount that you could hold isometrically is going to be a lot higher than that which you can press. Why is that? Muscle-wise. Because you have the maximum number of cross bridges occur and there's no movement. Right? You're in a physics, when you're talking about physics, you're in a much better position from a physics standpoint. Right? You're at the end of the range, the sarcomeres are as contracted as they can be, and you're just holding it. So where do they do this? So if you people do this all the time. Professional powerlifters do something called a heavy walkout when they're preparing for a meet, let's say on a squat, and what they will do is, let's say that let's say they're squatting 1,000 pounds. It's a nice even number. Okay? They could squat 1,000 pounds. They will actually walk out 1,100, 1,150 pounds. They'll put it on their back, and they will come out of the rack. They'll come up. They'll come out of the rack, and they'll actually walk it out. More than they can actually squat. Why can they do that? Because they're just holding it. Some of this has to do with joints and angles, and some of this has to do with the fact that the muscle is in the most opportunistic. It's at its strongest point. There's a weak point and a strong point for every muscle. All right? Every muscle has a weak point and a strong point. Right? And if you're only in the strongest part of that muscle, where it's most favorable, you're going to be able to hold maximum amount of weight, especially if you're not moving it. Right? So you may be able to, same thing here. You may not be able to bench 200 pounds. Let's say you could bench, I don't know, we're going to say 180 pounds. But if somebody helped you lift it into place, you could probably hold 200 pounds. Like this. And you could probably lower 200 pounds. You just can't press 200 pounds. You can actually lower more weight. Your muscles can actually lower more weight than they can actually press. So we're going to talk about, so that's called the eccentric portion of the muscle contraction. Eccentric muscle action. So that's what's going on here. Right? You can actually lower 15 to 20% more than the maximum. So this is very similar to the isometric. Same idea. Why is that important? So let's use a power lifter. So let's say that the power lifter is going to do a meet, he's shooting for 200 in the bench press, right? He's going to do something called negative. So this is not a scientific term, but it is a term that is used. They're called negatives. And what you do is you load the bar with 15 to 20% more than what you can push, and you have somebody help you out, and then you lower it. Now, when you get to the chest, you're going to have a problem, right? You're going to have a problem because you can't physically press this weight. That's why you have spotters. You have 2 guys, 2 girls, 1 on each side, maybe somebody behind you. They help you raise it back up, and then you lower it. You do this several times. What have we learned about that we're trying to desensitize? What are we trying to desensitize by doing that? Remember we talked about Golgi and muscle spindles? Which one are we trying to desensitize? Think about that one for a second. Which one are we trying to desensitize? So what do each of them do? What's the Golgi do? Yeah. Tension, the amount of force being produced. Okay? And then the other one does what?
Information about the stretching.
That's right. So what do you think's going on? Which one are you trying to desensitize?
Probably the Golgi,
Why?
because it's dealing with pressure and contraction. You're working on that as opposed to you're trying to hold it up as long as you can, as opposed to just stretching it.
Okay? Anybody have an alternative idea? Anybody say muscle spindle? What's a muscle spindle do again? Go ahead.
Doing negatives naturally the existing expression of the muscle. Trying to hold that at a latent position and slowly going down. Trying to resist the expression.
So what's probably the best answer? So you're both right. But you're not giving the best answer. It's the best answer. Both. You're doing both. You're desensitizing both of the receptors. Part of what's holding you back in strength is the fact that these backup mechanisms have been put in there to prevent you from tearing yourself to pieces. And they can be coaxed into desensitizing. And both of them sense both, right? But one is more stretch and one of them is more load. So you're doing both. You're getting the maximum stretch with the maximum load. So you're doing both. Okay? Does that make sense to everybody? How you can desensitize these receptors? So that's a practical application. That's what actually you do. Okay? All right. So if somebody would lower the lights, we're going to continue on. Yep. You have a question?
Yeah,
Yep.
it's on my graph. So why does the shortening velocity decrease if their load is the same? Am I reading that right? That the load
Here?
is between- Like across the whole bottom axis is like the axis, the load, and that's the line, so the load is retention. You see what I'm saying?
The velocity changes as the load increases.
So the load is retention.
The load is getting bigger. So if I put, this would be 0, let's say that this is 100.
So isotonic isn't the label on that axis.
No, the load, I should have put it under here. This is the portion of the isotonic contraction. I'm sorry, good question, right? This is the isometric contraction, and this is the eccentric that we just talked about, or the negative. Again, the negative isn't scientific. Yeah, sorry about that. That wasn't load, it's the load, right? It's getting bigger, the amount of weight. Good question. Okay. Okay, let's talk about muscle. All right, so the latent period, we're just going to show you this real quick. I know we've gone through this before. This shows the muscle fiber membrane potential, right? So this is when the action potential first starts. And then this time here is the time that the muscle contraction starts. So what Megan said in her explanation is that the latent period would get bigger because the time between the beginning of the action potential and the muscle contracting, in this case moving the weight, has to be longer as the load goes up. Now, in your book, there is a graph with the isometric, this is isotonic contraction, that this gap for an isometric contraction is smaller. And the explanation for that is that it's part of the setup. The setup that you have, and this is what the picture looks like. They don't have it in the lecture group. So the picture looks like this is a force transducer for the isometric contraction, and you're looking at this. And isometric contraction and the beginning of the latent period is smaller here. See that? See that? And that's because the force transducer, you take a muscle, you put it between two immovable objects. And then there's a sensor here. And when you start an isometric contraction, the sensor picks it up immediately. You immediately see it because the sensor does not require you to overcome the load in order to sense the contraction. Immediately upon the sensing of the contraction. Does that make sense? This says that the time between here and here is the time between that this muscle actually starts to move. In an isometric contraction, in this setup, the muscle isn't moving. The sensor picks up immediately. Could you have a sensor here that also picks up the contraction immediately? Yes. Yes. But here you're just showing when it actually starts to move. In the isometric contraction, there is no movement. So it is a function of the setup, the way we're measuring it. That's why the isometric contraction latent period is shorter than that of the isotonic contraction. Does that make sense to everybody? That it's a function of the way we're doing the experiment. Because in one, you're just sensing when any motor units are firing. In the other one, it's not enough just to sense the motor units. In the other one, you have to actually physically get movement. And that takes time depending on the load. That's the difference between the two. They explain it in the book. They may do a better job than I did, so you can take a look at it. We already talked about this. We did all of this. So, okay, something new. We've sort of talked about this motor units. So here you have a motor neuron that's attached to 5 muscle cells. Here you have 2 motor units. One is made up of 1, 2, 3, 4, and this orange one here is made up of 1, 2, 3. Okay. So a couple of different things going on. You have in your muscles all kinds of different size motor units. Right? Every muscle has multiple sizes for motor units. You don't all have one size fits all. Does that make sense? So there are things that we do, right? So when I am picking this up, right, gingerly, I don't want to break it, the bottom comes off of this thing, right? I'm picking it up with these 2 fingers, right? These are the 2 strongest fingers. Well, it's actually these 2, depending on the movement. But these 2 are also very strong. These are the 2 strongest fingers if you're doing this, these 2 if you're pinching. Okay, so these are the 2 strongest fingers here, right? When I do this, do I need to apply a lot of force? No. So am I going to activate a big motor unit that maybe has 100 muscle cells attached to it? Why would I do that? That doesn't make any sense. But if I had a load here, if I had a block, I should have brought it in because I have one of these in the lab. I could have brought it in. It's called a block weight. If I had a block weight in here, it's basically the end of a 50-pound dumbbell. We just hacked part of it off, so it weighs 25 pounds. That's all it is. And I did this, and I put my hand on it like this. Could I recruit the same number as this? No, I'd have to recruit more, right? And I'd have to recruit bigger motor units. Biceps have the same mix, the quadriceps, the hamstrings, the abdominal muscles. There's this mix. There's large motor units and there's small motor units. You always start from the bottom. You use only as many as you need. So you're going to start with the small motor units first. Does that make sense? And as you have to apply more and more force, you will go up in the size of the motor units. But when that's not enough anymore, then you're also going to start recruiting multiple motor units, big and small. So you start with the small ones. When all of the small ones are recruited, you go up in size, and you may actually recruit multiple small ones and multiple medium ones and then multiple big ones. And for a true maximum effort, you recruit the maximum number of motor units in every category. All of them fire. So what we're seeing here is these would be considered very small motor units, tiny, right? 4 or 5 muscle cells. So when this motor neuron fires an action potential, all of the muscle cells that are attached to that motor neuron fire simultaneously. It's all or none. So not only is the action potential here all or none, but the activation of everything that's attached to it is all or none too. You can't this motor neuron does not have the ability to send, well, I only send a signal to this one, and I'm not going to send a signal to these 3. That's why you have to, nature designed you to have multiple motor unit types. Really, really small ones, really, really big ones. And they can work individually, and you always start with the minimal, and you keep going up in size until you get to the maximum. questions on it? All right, so this is something else. This looks at, we're going to look at this when we get to smooth muscle in the heart. So what the heck is this? So this is a plasma membrane. All right, this is a plasma membrane. This is a T-tubule. This is dihydropyridine. Okay. Remember when we looked the other day, I take you through excitation, contraction, coupling, and we did skeletal muscle first, and then we did cardiac, and we're going to come back to smooth muscle. When we're talking about the differences between them, and they're written down. I wanted to show them to you. So this is different right here. So this part, all of this is the same as skeletal muscle. What's different is these calcium channels. Remember I told you that there are calcium channels in the plasma membrane. And then there are these calcium pumps, calcium exchangers, and then there's also the sodium potassium ATPase. So this and this don't exist in skeletal muscle. This doesn't exist in skeletal muscle. This doesn't exist in skeletal muscle. So this is a picture of what actually happens. And the other thing I like about this picture is that this picture actually shows you what happens to the beta 1 receptors when epinephrine or norepinephrine binds to your heart muscle. Remember, this is happening in the heart. And this shows you the molecular pathway on how you amplify the signals here. One other thing that I didn't talk about, and the phospholambin here also occurs in skeletal muscle. The phospholambin, all right, the phospholambin actually speeds up the calcium ATPase, the circuit pump. Okay, so that means you can get the calcium that has been spread throughout the muscle cell back into the SR faster. Why would you need the calcium to go back into the SR faster if you have epinephrine or norepinephrine bound? What's the big picture response? What does epinephrine and norepinephrine binding to the heart do? Big picture. Person on the street picture, not person in my class picture. Right? What does that do to your heart? What do you think? Yeah.
Increase your heart rate.
It increases your heart rate. It also increases something called contractility. So your heart can actually beat faster. So then why do I need to upregulate phospholambin? What's being able to make this circuit pump here move faster? How is that going to help my heart beat faster? And so you're not going to think big picture. By getting the calcium back into the SR faster, what can happen faster? The heart will beat faster because now you can then release the calcium again much more quickly. If you don't get the calcium back in, then you don't have much of a gradient here, right? You have to keep that massive gradient. So you have to make the circuit pump move faster, right? You gotta get there with the whip. Come on, you need to move faster because we need to contract faster. And we're dependent on the calcium. Now, is this the only thing that we're dependent on? No, because we've got these two, right? And so there are also things going here because this plasma membrane calcium ATPase also has to work faster. Does that make sense? It's in order to speed up or to make a contraction stronger, you not only got to make the positive part of this faster, but you got to make the negative part. So you got to make the repolarizing as fast as the depolarizing, right? You have to recover as fast as you have the action occur. If not, that's going to be a bottleneck, right? You're limited by how fast you can get the calcium back in and out. And then that is now ready to go again. And it happens very, very quickly. So I wanted to show you, because a picture to me helps. These are some of the differences we talked about the other day. Does that make sense to everybody? Yeah. Go ahead.
Can you just repeat what different channels are in cardiac and aren't? So
Yes. So this is the heart, right? This is cardiac pump. This is not skeletal muscle. Okay? If you draw this picture on an exam and say this is skeletal muscle, I'm going to take a big old red X and put it right through it because it's not. Right? So the differences are that in this you have calcium channels that bring calcium into the cell. These calcium channels do not exist in skeletal muscle. Okay, so these two, there's one here and there's one here. Different. That's one major difference. Okay. This calcium pump in the plasma membrane, because this is the plasma membrane of the muscle cell, the sarcolemma is what it's called, right? This doesn't exist in skeletal muscle. Doesn't need it. And then the sodium-calcium exchanger, which works on secondary active transport, right? Because there's a huge gradient here between the outside and the inside of the cell for sodium. So as 3 sodiums come in, if you bind the calcium to this, it will shoot the calciums out. So this is an example of a secondary active transport mechanism. And then this exists everywhere. The sodium, potassium, ATPase exists everywhere. So this is the same. So those are the 3 major differences between the two. And it's a difference because the heart gets most of its calcium for contraction, this is a super important point, from the ECF and only some from the SR. Skeletal muscle gets all of its calcium for contraction from the SR. So it doesn't have to deal with the ECF concentration at all. It's non-relevant. Okay, good questions. This is just another example of the neuromuscular junction. We're not going to talk about this because we already have it. Right? This is all for you. A lot of what I just went over in that sheet is here. This is their version of the excitation and contraction coupling. Use mine. Mine's a little bit more detailed. This is the showing the difference between an isometric contraction and an isotonic, and you can see that in the isometric contraction, the latent period is much smaller, and that's because of the way we're doing the experiment. Because of the way we're doing the experiment. Right? Because in this one, you're moving a load, a weight. In this one, this is locked down and this is locked down, and the sensor picks up any motor unit movement at all. Here it doesn't pick up the motor unit movement until the actual weight starts to move up. Here, this will never move up. Okay, so some of the terms here. Iso, remember, means the same. Tonic means the same tension. In this case, the amount of force that's being applied is the same. So tension and force mean the same thing, and metric is the length. So this is an isotonic contraction, right? There's other types of movement-oriented contractions. There's isometric, you don't move. There's isotonic, right? There's isokinetic, same speed. So there's different kinds. You can, when you move a load, you can keep the force the same, or you can keep the speed the same. So an isokinetic contraction means that the speed is the same, but the force being produced may actually be bigger to keep the speed the same, or it may be less to keep the speed the same. So in isokinetic, you think about it like the cruise control on your car, right? You set the speed. You set it at 50 miles an hour. When you're going downhill, the engine and everything associated with the braking system has to back off. The braking system has to maybe come on, the engine has to back off, right, on the downhill in order to keep the speed. When you're traveling flat, that's sort of the middle of the road. But when you're going uphill, and when you've used one, and you use the cruise control on a car, have you ever noticed what happens in an older car when you start going uphill? What happens to the speedometer as soon as you get to the bottom of the hill and you start climbing? It will in the new cars, because you guys have the new fancy ones that are reactive, but in an old car, what you would actually see is as soon as you hit the bottom of the hill, the speedometer would actually come down. And all of a sudden the sensor would kick in and say, oh, we're slowing down, and it would go up. In the cars that you're probably used to either driving or your parents have, the technology is so much more sensitive that that doesn't happen, right? So you may actually see it anticipates the hill and all actually starts to go up before you hit the hill. That's a different system. But the old ones, you'd see it go down 5, 6, 7 miles an hour, and you're like, oh, what's going on there? And all of a sudden you hear the transmission change gears, go down, and go, and then it comes back. And then it may actually overshoot it. The human body does the same thing, right? There's different levels of sensitivity. Okay. This is another important curve here. This one is taking a look at the distance shortened in millimeters over the time in milliseconds. And what's important is you have a light load, an intermediate load, and a heavy load. The light load is green, the intermediate load is orange, and the heavy load is purple. So what's the important, if I had to say to you, what's the important take-home message of this graph? What do you think the important take-home message would be? What would you focus on this graph to tell you the story about load and velocity? Or this was a question asked the other day, right? What would happen to the amount of force production? What would happen to the amount of force production if you had, as the muscle shortens? Actually, maybe on your exam. It seems like the other day for me. Anybody guess? All right. So, as the load goes up, the slope decreases. It's the slope of the curve that's the most important thing. So all you really need to pay attention to, the fact that the distance shortened is different, right? Because this is heavier than this, it's all about the slope, right? This is the fastest speed, this is the next fastest, and this is the least. And that's what we said before. And we showed it with this curve. Same thing. This and this are essentially one and the same. They're just looking at the data a different way. The bottom line is, as the load increases, as you move more and more weight, the velocity slows down, right? Because it's distance. Velocity is distance over time, right? Miles per hour, meters per second, kilometers per minute, right? Millimeters per millisecond. This is the velocity. So some people prefer this curve to this curve, but they're actually showing you the same thing. That's important. Okay, it's very important. Showing you the same thing. Questions? And all three of these are isotonic. If they're different types of contractions, you'd have to make different graphs for them, right? Isokinetic would be different than isotonic, different than isometric. They have to all be the same, or else you're comparing apples to oranges, right? You want to compare apples to apples here. All right, this is just showing you what happens with the twitch and tension. We've already done this with the neuron. Remember that when we looked at the neuron? So here what we're looking at is what's called a twitch, a muscle twitch, which is essentially one contraction. Right? You have a motor neuron that activates a muscle. Let's say there's one muscle cell, and you get tension produced. You have one motor neuron also attached to one muscle cell. You get another twitch. You get this. If you start to apply the next threshold stimulus before the recovery occurs, what happens here? Assuming you add the same stimulus. Didn't we see this with neurons too? You actually get a greater stimulus. So one of the ways to make a muscle stronger, and we talked about this with neurons, is to make it fire more frequently. The more frequently, the faster you fire the muscle, the stronger it gets. To a point, and then it'll plateau until you get tetanus. right? Tetanus would be a plateau, would come up like this and just stay there. That same, if you understood that for motor neurons, it's the same thing. So a lot of the principles that apply to the nervous system also apply to skeletal muscle and the cardiac muscle and smooth muscle. They're the same. You can't separate them, right? Because this, the muscle, relies on the nervous system. Does that make sense to everybody? Yes? Same thing. So if you understood it then, you should understand it now. Okay. So here's some explanation. It says, complete dissipation of elastic tension is subsequent to stimuli. There's also an elastic tension here. There's also what's called a passive and an active force. Okay, we're going to get to that too. In S3, occurred prior to the complete dissipation of elastic tension, so you get another contraction that is now stronger. And then here, if you apply them even closer, you get a contraction that's even stronger than that. Right? Tension is force. This is the strength. Tension, force, strength. So this is what's called temporal summation. That's when you activate a neuron or a muscle cell more frequently. You increase the frequency of stimulation. The technical term is called temporal summation, meaning time. Here you're looking at unfused tetanus. So you can use the same thing, right? You can start firing it more and more and more. This is called unfused tetanus. And then if you start applying the stimulator at a super high rate, which hopefully you did in PhysioX, eventually you get the maximum amount of force, and then it tops out. So this is exactly what tetanus, the disease, the condition would look like too. Except this you're doing artificially. You can also do this for yourself. If you will it so, if you want it to be so, you could lock the muscle up. I've done it. Right? If there's something called mind-muscle connection. If you're totally in the zone, and I've done it. I've locked the muscle up. I can't get it out. That's how much of force I've been applying, and that's how much the connection is. And sometimes it hurts like hell. Okay? It's possible to do it. So the bacteria could do it, toxin. You could do it, or you can have an electrical stimulator hooked up to a muscle that can do it. So there's 3 different ways it can occur. All right, another super important graph. This one is looking at one sarcomere. Remember, the sarcomere is the functional unit. The sarcomere is the functional unit, and this is the last thing I'll do. The functional unit of muscle. This is the percent of maximum tetanic contraction. Tetanus is the maximum amount of contraction you can get. This. Can't get any more than that, okay? And this is the percent of the muscle length. Okay? This is the percent of the muscle length. This is 100% of the muscle length. This is 60%. This is 170%. Okay, my bicep right now. Which one of those percentages is my bicep at right now? In the position that my bicep is in right now, which one of those percentages is it in? Jacob? It's 100%. Can I get my bicep much beyond 100%? Yes. A little. But much beyond? Depends on how mobile you are with your ligaments and joints. Some people can. Like I'm wound up tighter than I'm wound up pretty tight. Okay, I don't have much room. The way we could do it though is we could just take a surgical scissor and go in here and cut, and then we can get it to go to 170. Right? So everybody should be able to go with your skeletal muscles from here, maybe a little bit over here, down. From here out, you can't. Not in skeletal muscle because you're attached to bones. So you got to snap the connections. Take a knife and we hack here so that my biceps tendon gets dislocated, cut from my bones, I can go to 170. Other than that, not so much. So you're going from here down. Why are they showing this? Because if you do this experiment, and we do this with rats, where you use that transducer system, where the muscle ends are not connected to muscle, right? I'll show you. Here. So if I took my bicep and I cut it out of my arm, and then I put it in here, could I do this 170% length thing? Yeah, and they did, and that's how they figured this out, right? But you could never do it in human. That's a lie. You wouldn't want to, be me. That's what they tell me. Okay, so this is really, really important because what does this tell you about? This is 100% is called the resting length, and this resting length in skeletal muscle is also the same as optimal length. Now, the reason I'm telling you that is very, very important because when we get to the heart and we get to smooth muscle, the resting length and optimal length are not the same. My resting length, this is where your bicep should sit, right? Everybody agree? If I took all of you and made you stand up and you stood in the anatomical position, would not all of your biceps hang at 100% of resting length? Unless you have something wrong with you, yes. So that means that that is the maximum amount of force. That's the place you want it to be in when you start a contraction. Because according to this, that's where the maximum amount of force can be contracted. What happens as it starts to get shorter? What if I make you start a contraction from here? Can you lift as much weight in the graph? No. What if I make you start from here? Can you lift as much weight? No. And then if I go in the other direction, can you lift as much weight? So in this white zone, it's the resting length equals optimal length, which is the maximum amount of force production. And this is what each of the sarcomeres looks like. All right, before we go, I got your exams. Turn the lights on, please. Real quick. All right, we're going to go fast. All right. I should have stopped a little earlier. That's all right. All right. I'm going to go fast. Explanations. We're going to hand them out. Okay? Everybody ready? Go. All right. So, for those of you who haven't had me before, this is the way I do it. So. It's not good. All right, averages. 10, 11, 12, 13, 14, 15, 16. You're 16. These are years. 83.74, 69.5, 80.92, 82.03, 79.6, 74.5. Not good. Okay? That's both sections combined. All right, I'm going to hand them back to you. You can look them over. You can make voodoo dolls, burn me in effigy. All right, we're going to split since you're new to the class, split the deck. Okay? Split it. There you go. You don't have to do it. All right. Wrong section. Okay, so shall we take a look at it, everything, add it up, make sure it's right. Dominic, it's Amanda, Corey. Courtney, Michael. Lucas, Amanda, Adriana, Alex, Andrea, I know you're not. You I know for sure. Here, Josiah, Marissa. All right, hold on. Trying to switch the view here. Everybody got it? Do the math. Look over the answers. Let me know.
As strong as I thought.
No, you're actually better than the average, right?
Yeah, but I still got the next one. Show you that.
I know what you're capable. You don't have to tell me. I know what you're capable of.
Just a little, I guess.
I'm not.
What's the,
I have no delusions that you're not capable of more than that on so many different levels. You haven't lost any of my respect. Trust me.
Just a little vote of confidence.
It's just it is a learning experience, right?
Yep, they all are.
They all are. Don't you worry. Hey, how are you?
Good. For an lit review, how long should the annotated bib be? I drew a paragraph. Do you take the Google Docs sometime in your life to this week and see if it's like suitable? I did one.
The one for the research.
Yeah. How long should it be? Like a paragraph or longer?
No, more than a paragraph, then you're wasting time.
So just a paragraph.
Yeah, because you don't want to do that, because the whole point of the annotated bibliography is so we can quickly scan through it and say, okay, what